This is problem 21 of the QHack 2023 Quantum Coding Challenges, and this one is entitled A Pauli-Worded Problem. Now I would say this challenge is probably one of the hardest problems in the whole series, specifically because we need to understand a lot of different concepts to be able to solve it. So what I want to do in this video is go through each of these different ideas that we need to understand, and then start coding things up in PennyLane. So the first important concept that we need to be familiar with is that of the Pauli decomposition. And I'm not going to spend too much time on this because I have a whole video series on the density matrix and mixed states, and specifically a video on Pauli decomposition. So I'll just add a link in the description below if you're interested in learning more about it. But the bottom line is that we can express any density matrix row as a sum of Pauli matrices, here denoted as P sub I, multiplied by some coefficients, here denoted as A sub I. And these P sub i's are basically tensor products of the three Pauli matrices X, Y, and Z and the identity matrix. So for example, for 2 qubits, this summation will be for all possible combinations of these 4 matrices. So it will be I tensor X, all the way to Z tensor Z. Now in this particular problem, we're given this same expression but using a slightly different notation. So we're told that any density matrix row can be expressed as the sum of this row sub p's. This row sub p's are basically Pauli matrices expressed in this form. So it's very similar to what we have above, but here we're expressing it with this 1 over 2 to the n plus the identity matrix plus this p, where this p is just the set of x, y, and z. So it is the same idea. It's just separating the identity from the Pauli matrices. And again, in this particular case, here this set of matrices represents all possible tensor products. So for 3 qubits, we could have XXX, 4 qubits X, Z, Y, Z, and so on and so forth, right? So that's the first thing we need to know, that we can represent any density matrix as sums of these Pauli matrices with some coefficients. The next important concept we need to know is that of depolarization noise. So in the case of a 1 qubit system, we express depolarizing noise in the following form. So we have some coefficient lambda, and with probability lambda, our density matrix rho turns into an identity matrix. So if lambda is, for example, 0, then in that particular case, we just have our original density matrix, so no noise. And if lambda is equal to 1, we have the maximum amount of depolarizing noise. And then, well, if this is 1, this will go to 0. And then all we have is an identity matrix. And anywhere in between, we would just have some mixed state of our original state and the identity matrix. Now, this is for 1 qubit system, but we can generalize this for an n qubit system. And in particular, we can say that for a Pauli density matrix rho sub p, we're just going to use this notation of rho sub p of lambda as a Pauli density matrix where we have applied depolarizing noise for n qubits. So it doesn't have to be necessarily a 1 qubit system. Now, similar to for the 1 qubit state, the more noise we apply, so the larger the lambda is, the more this rho sub p of lambda resembles the maximally mixed state. So basically, it gets closer and closer to an identity matrix. Now, the next important thing we need to know is that because any row can be expressed in terms of sums of these Pauli density matrices, the same can be said about rho. So basically, we said that the more noise we add, the more this rho sub p resembles a mixed state. Well, the same can be said of a matrix that is composed of these rho sub p's, right? Of a summation of different rho sub p's. All right, now the next concept we need to be familiar with is that of the trace distance. And the trace distance is given by taking the difference between a density matrix rho and sigma, computing this norm where this norm is given by this expression right here. So the square root of the transpose conjugate of this subtraction times the value of that subtraction, and then taking the square root, and then taking the trace of that result and multiplying by 1/2. So that's just the definition of that trace distance, and that's just a measure of the similarity or of how different two density matrices are. And then we can use this concept of trace distance to compute the bound of the difference in expectation values. So if we take a look at the difference in expectation value of some projective measurement M on density matrix rho and the same measurement on the density matrix sigma, which this difference is given by taking the trace of the measurement of the difference of the two, this trace distance bounds that result. So we know for sure that the difference in those measurements is smaller or equal to this trace distance that we can compute using this equation right here. So basically we can use this value to see how hard it is to tell apart the measurement between these two matrices. So it's a measure of how difficult it is for us to distinguish these two states from each other for any given measurement M. Okay, and then lastly, what we need to also understand, and I'll be honest, I have not looked into this very carefully. I don't understand exactly where this comes from, but we're told that for some depolarizing noise channel, given some probability lambda, taking the trace distance between the noisy density matrix of a Pauli string with respect to the maximally mixed state rho sub 0, that value is bounded by this expression here, 1 minus this lambda to the power of this p, where this notation just indicates that this is the number of non-identity operations in the word p. And again, I don't know exactly where this expression comes from, but basically this will be easy to compute, right? We are given this value of lambda. We know what the word, the Pauli word is, and we can check how many elements in that word are not identities, and then we can compute the number, and we're told that that bounds this trace distance between the noisy density matrix of our Pauli word and the maximally mixed state. So what we're asking this problem is to actually compute the difference between this value and this value, and since this needs to be smaller or equal than this, then that means that the difference of those two has to be smaller or equal to 0. So again, to recap, we need to understand that any density matrix can be decomposed in terms of summations of Pauli strings. We can denote the depolarizing noise of one of those Pauli string density matrices in this form right here. And we can use the trace distance to compute how different a noisy density matrix of a Pauli word is from the maximally mixed state. And then we can compute the difference between that calculation with this expression that is given to us here to show that this is smaller or equal to 0. So that's what we're going to do next. So as always, we import PennyLane as QML, NumPy, and here we're going to import SymPy because we're going to be given some helper functions to calculate some of these different parameters that we're going to need. So the first one of those is a function that calculates the distance between two density matrices rho and sigma. So this function right here is basically to help us compute this right here, this absolute value or norm of rho minus sigma, which is given by this expression here. Then we're given another helper function that helps us compute the number of operations in a Pauli string that are not identities. So basically this function right here is to help us compute this value right here for the exponentiation of this equation. Let me rewrite it down here. So this function is to calculate just this part right here. And now the first thing we're going to do is implement a function to compute this density matrix rho sub p of lambda for some given word p. So we're going to define a function. We're going to call it noisy Pauli density, which is going to take in a word. This is going to be a string of x, y, z Pauli matrices and some parameter lambda. And first we need to compute the number of qubits, which is basically equal to the length of the word. So in a Pauli word, each term denotes the matrix applied to a given qubit. And then we're going to make use of this Pauli-Word function in PennyLane that, if we see here in the documentation, it takes in a dictionary with the key representing the qubit and the value representing the Pauli matrix that we want to apply. So before generating this, let's create that dictionary. So let's call it word dic. And what we're going to do is use a dictionary comprehension where the key is going to be the number in the Pauli word, and then the value is going to be the letter of that Pauli word. So let's just take this and put that in another cell, and let's just do an example here where our word is, for example, x, y, z, z, x, and see what this generates. So here we see that on qubit 0 is applying x, on qubit 1 is a y, on qubit 2 a z, qubit 3 a z, and qubit 4 an x, right? So that's basically what that word represents. And then we're gonna create an identity dictionary, which is basically of the same length as this word dictionary, but just with identities. So basically that is going to allow us to generate this rho sub p's, right? So we said that this rho sub p's are composed of the Pauli matrix on the word plus an identity matrix for each element. So we're going to combine these two together to create our Pauli density matrix rho sub p. So this Pauli word 1 is going to take this identity dictionary, and then we're going to create a Pauli word 2 that is going to take the word dictionary. And then in PennyLane, we can use this Pauli sentence function that takes in Pauli words with some coefficients and then generates a sentence such as the one we want to create. So here what we do is use QML Pauli sentence and pass the first Pauli word, which is the identity, with coefficient 1 over 2 to the n qubits, and this has to be a dictionary. So let me just put that here. And then this Pauli word 2 with the same coefficients. Now, after creating our Pauli sentence, we need to turn that into a density matrix. So for that, we can use this qubit density matrix that takes that Pauli sentence, which has this method toMat, which converts it to a matrix. And then we just need to pass the number of qubits. So right now we have created an ideal density matrix for a Pauli string. And now we need to add the noise. So to add the noise, we just do a for loop for the number of qubits we have using the depolarizing channel function that takes the probability lambda and then the qubit. So we're applying it to each of the qubits in our system. Okay, so that created our noisy density matrix for a Pauli string. And now we need to create the function that is going to compute the trace distance between two matrices. So our noisy density matrix of the Pauli string and the maximally mixed state density matrix. So we're gonna call that max mix trace distance that takes in the word and lambda. Again, we're going to define the number of qubits, which we're going to need to define our device. So for the device, we're going to use default mix like we did last time. And we're going to define a Q node. We're going to call it row, which is going to call this function that defines our noisy density matrix for the Pauli-Word, and then returns the density matrix of that. And then we're going to define the variable row, which is just basically the output of this function. And then sigma is going to be the density matrix of that maximally mixed state. So we have 1 over 2 to the number of qubits times, we can use this numpy I function to define an identity matrix of 2 to the n qubits. And then this whole function needs to return 1/2 times the trace of, we're going to use now this helper function that calculates the distance between these two matrices, right? And if we go back here, that's just computing this trace distance, right? So 1/2 times the trace of that distance between rho minus sigma. And lastly, we're going to define another function called bound verifier that takes again the word and lambda, and it's basically going to return what we're being asked, which is basically the difference between the trace distance of our noisy Pauli-Word density matrix and the maximally mixed state density matrix, and this parameter 1 minus sigma to the number of non-identity operations in the Pauli-Word. So we're going to do 1 minus lambda to the power of the word distance. So this is a helper function that we're given that calculates the number of non-identity elements in our word, minus this max mixed trace distance of the word and lambda. Okay, and now let's define our inputs. So we're given 4 inputs here, and we just need to call this bound verifier function and then pass that input. So let's do it for input 1. So we get 0.0877, and if we go here, we can see that for input 1 we get 0.08777. For input 2 we get 0.4035. Then for input 3 we're supposed to get 0.30999. So here we have it. And then for input 4, it's going to take a little bit longer because this is a long word. We get 0.229. And then here we can see that for that long word, we're supposed to get 0.229. So that just shows that we have implemented all the right functions. Once again, let me know if you have any questions.